Ooh. Ooh.
What's wrong with you?
I'm just stuffed.
Why?
I ate an entire radical.
Yeah, and that's the best intro we could come up with.
I'm so sorry.
Me too. Speaking of entire radicals are like the radicals we saw in the previous section, right? They have those three main components. They have that root or radical symbol, they have the index, and they have the radicand. Nothing else. So like the cube root of 17, the square root of 92. Those are entire radicals. Now, it is sometimes possible to reduce or simplify these entire radicals by extracting a part that has an equivalent whole number value. Okay, so what I want you to get out of this first little section are these two words that should cue you to then convert an entire radical to a mixed radical. And that's what this whole lesson is going to be about. But if you look at your task instructions, so number 4, reduce radicals. Reduce the radicals. Simplify the radicals.
Or
just
voice.
Simplify. No.
Sounds like my voice.
It's my generic man voice.
Oh, okay.
But that will be, those will be your action words to then perform the task we will go through this unit. Now, before we even do that, we're just going to kind of see what we know that might be similar to what we'll be performing today. And what we know is the following property of exponents. So if we have two things multiplying together, taken to a certain power, we can distribute that exponent to both terms to get a to the power of n times b to the power of n. So each of those two factors will then be taken to that exponent. In the same way, if we have two things multiplying in the radicand, we can apply the root or the index and the root sign to each of those factors. So we can, factors. So we'd get the nth root of A multiplied by the nth root of B. Now, some of you might be thinking, great. Why is this important? And I was actually just about to tell you, so prepare yourselves. Why is this important? Well, if we're able to distribute it, or that index and the root sign to each of those factors, we might do so strategically so that we can actually turn one of those factors into a whole number, something that will have a rational root. So let's take a look at what I mean, because sometimes things can get a little bit confusing. All right, we are going to look at the square root of 40. And the square root of 40 is an entire radical because it just includes the index, which is secretly a 2, a radical sign, and the radicand. That's it. But we want to turn it into a mixed radical. So what we're going to be doing is we're going to try and find two factors of 40 in which one of them is a perfect square. Why is it a perfect square? Because we're dealing with square roots here. So we're going to be looking for factors of 40 in which one is a perfect square. And looking at that, 1 and 40, yeah, I guess 1's a perfect square, but that's really not going to help us anywhere because we still have 40. 2 and 20, none of those are perfect squares, so 4 and 10. And you can see this is already on the page, so you can assume that it works, but it works because 4 is a perfect square. And we want one of our factors to be a perfect square, because if it's not, everything we're doing would be worthless. Anywho, so we can rewrite the square root of 40 as the square root of 4 times 10. Nothing has changed because 4 times 10 is the same thing as 40 to begin with. Now, this is where we look at that similar exponent law that we just spoke about, right? If we have a square root of 4 times 10, it's equivalent to saying the square root of 4 times the square root of 10. Okay? So we could break it down into two radicals being multiplied by each other. Now, the whole purpose of why we did this, and especially with our perfect square factor, was, hey-o, the square root of 4, that's equal to 2. So instead of writing the square root of 4 times the square root of 10, we can write 2 times the square root of 10, which gives us a mixed radical. I was going to say mixed fraction. Mixed radical. Ooh. Everyone now. Ooh. So our mixed radicals will have some whole number component being multiplied with the remainder of my radical that's left over there. And when I'm looking at these, I always want to make sure, well, does 10 have any factors that are perfect squares? Because maybe I didn't take out the biggest perfect square in the beginning. And no, my factors are 1 and 10. 1 won't help me. And 2 and 5. And 2 and 5 aren't perfect squares. So I know I'm in the end zone. All right. So we're going to take a look at some examples here.
I will start, and I will start with this one. So fully reducing this, I'm going to break up that 12. I'm going to break it up in this reddish color. No, green. And I want to break it up into a part that has a square and a part that's not. So 6 and 2 is no bueno. That does not help me. But 4 and 3 does, because 4 is a perfect square. From here I can say that we've got the root of 4 times the root of 3. So we're splitting it to its two components. The square root of 4 I can evaluate as 2. The square root of 3 I can't. So its exact form is just straight up root 3. And with that, this example is done. I encourage you to try the other 3 that are on this page. If you're really feeling daring, you can, I suppose, try the next page too. But try these 3. Pause, boop, restart, boop. Here I go. I don't know how to scroll anymore. Figured it out. Square root of 80. I'm sure square numbers go into this. I know 4 goes into this. So I can say this is 4 times 20, which is then the square root of 4 times the square root of 20, which gives me 2 root 20. But worth noting is that the root of 20 is not fully reduced. So it still has a square number that goes into it. Let's continue then. So this 2 I had is going to stay same. And the square root of 20, I'm going to break up into 4 and 5. This 2 again is same. I've got this root 4, and I've got this root 5. In my next line, I still have this 2. The root of 4 is also 2. And then the root of 5 is just root 5. Can't be simplified. So my final answer will have 2 times 2 for the whole number part, which is 4. And then root 5. The necessary steps to show in this, if you want to go the fast way and say that 80 can be broken up as 16 times 5, that'll be faster for sure. But if you're going to show a whole bunch of steps, I would say you have to show one of these. You'd have to show this. You'd have to show one of these. And then for sure you need this. And for that previous example, you for sure need to show one of these. And then of course your final answer, which is this.
Ooh, me! Yes. All right. So taking a look at this next example, we have the square root of 72. And my brain immediately sees the factors of 36 times 2. And maybe you guys didn't see that. Maybe you guys did. Sometimes my next go-to factor, if I'm looking at 72, would be 9 times 8. And thinking of that, well, 9 is also going to be a perfect square, just like 36 is a perfect square. Both will get you to the same final result, but just like Mr. A showed you in the previous example, if you don't collect the biggest square root at the beginning, right, because you could have done 16 times 5, it's okay, you will still get to the same answer, it just might take you a little bit longer. Okay, so no fret. But here I have the square root of 36 times 2, which is the same as the square root of 36 times the square root of 2, which will give me 6 times the square root of 2. Okay? And last but not least, 150. So if I'm looking at that, my go-to head brain answer is 25 times 6. So I'm going to see the square root of 25 times the square root of 6, which is 5 root 6. And again, like Mr. A was saying, you only need to show, oh, that's ugly, one of those two as well as your final answer. And it doesn't matter which one you show as long as it's one of them. All right, so take a look at this next page here. So when we're talking about writing a radical and simplest form, so we are going to keep reducing it until we can't reduce no more. It's kind of like shop till you drop, but simplify until you can't simplify anymore. Simplify. So like the better version, because you get knowledge instead of things. All right, so for example, if we were looking at the square root of 32, yes, we could simplify it to be 2 times the root of 8, but that wouldn't be fully reduced. So the correct final answer, the one that will get you full marks in a situation like this, would be 4 root 2. So even though those all of those values are equivalent, they're all equal to each other, we want to make sure that things are in the simplest form, right? Kind of like if we had 8 over 4, we could theoretically just go 4 over 2 or 2 over 1, but we're looking to simplify it to the most simplistic form, which is 2. So in the same sense, we want to simplify it to its most simplistic form here as well. So always make sure as you're working along that you check your final answer and think to yourself, okay, hold up. Are there any more perfect squares that can go into my final radicand? And if there are, keep trucking. And if there aren't, box your answer, call it a day.
We just took a look at simplifying square roots, but we can also simplify cube roots or anything that's higher order, so like an index of 4, 5, 6, 7, 8, 9, 10, 11, 12. When we do that, we'll want to be noting what that index is as a key for how to break up the radicand. With a square root, we always wanted a square and something else. With something like a cube root, we want to break things up into a perfect cube and something else. So breaking this up into 27 and 4 helps us, not because 4 is a square. Squares are irrelevant when we're dealing with cubes. But it helps us because the 27 is a perfect cube, and we can reduce the cube root of 27 into a whole number. Cube root of 27 is just 3. The cube root of 4, we can't reduce that. That's just cube root of 4, so that's done. Try these ones out. I will. I know, for example, that 40 can be broken up into 8 and 5. I used 8 because 8 is a perfect cube, and I'm dealing with cube roots. So I can say this is the cube root of 8 times the cube root of 5. The cube root of 8 I can evaluate. That's 2. And the cube root of 5 I can't do anything with. Ms. T had mentioned at some point earlier, can't remember if it was this lesson or previous one, just making sure that the index goes right in this little nook here of the root symbol. And that's particularly important now where we don't want to accidentally say that we've got 2 cubed times the root of 5, right? There's some ambiguity here. Gross. Don't like. Clearly defined results.
We also want to make sure that our index is little itty bitty. We don't want to go something like that.
23rd root of 5?
Right? It's super unclear. Is the 3, I guess the 3 is inside the radical symbol, but at the same time, it's the same size of the 2. Ugh. So you want to make sure that your final answer is clear to us so that we can appropriately evaluate you on your work. Alrighty. Taking a look at this next one here. So we're looking for perfect cubes that are factors of 54. And when I look at this, I think a little bit because it doesn't come right away. But then I go, yes, that must be 27 and 2. And again, I chose 27 because 27 is a factor of 54, but also it is a perfect cube. And that's important because we're dealing with cube roots. All right. So as I do this, I can rewrite that as the cube root of 27 times the cube root of 2. The cube root of 27 is just simply 3. And the cube root of 2, well, it's the cube root of 2. Whoop-de-doo. And I'm going to look at my final answer, look at the radicand and be like, well, where'd it go? But I'm going to look at it and go, hey, does it have any remaining factors that would also be perfect cubes? Because I want to make sure that my final answer is fully simplified and not just partially simplified. But we good here, so we are going to call it a day. Actually, we're going to call it next example. Ooh. So if I'm looking at this next example, 72. Remember we did that one last time with the perfect square. Of course, I'm thinking again, my first factors that come to mind are 36 and 2, but those aren't going to help me this time.
Yeah.
They've abandoned me.
Oh.
36 is not a perfect cube, and 2 isn't a perfect cube, so, well, I have to look for something else. And here I go, and as I look, I'm going to think, my second factors, well, what about 8 and 9? You know what? Just for the sake of spicing things up in this example, I'm going to write 9 times 8. I'm not going to write my perfect cube first.
Gracious.
Now, if I do that, I'm going to get the cube root of 9 times the cube root of 8. Great. The cube root of 9 is not simplifiable in this case because, remember, 9 is a perfect square, not a perfect cube. So here we have it. And then I have times by 2. Now, this answer, if we think back to when we were talking about variables like 2x, we never wrote x2.
Ugh.
Yeah, right? And we never wrote pi 6. We always wrote 6 pi. There's an order to things, a preference, some sort of way to make all mathematicians in the world go, it's beautiful. And that is to make sure that when we're looking at mixed radicals, we always write the whole number first. So our final answer should indicate that whole number 2, and then the rest of our radical. It's beautiful. See? All of the mathematicians in the world did this, even in their sleep.
You want me to add a chorus effect after, so it sounds like it's a lot of mathematicians at once?
Good, perfect.
I'll do it. All right, last example. The square root. No, I'm not dealing with square root. Cube root. No! My goodness, it's a 4th root. I don't know a ton of perfect fourths. I could probably tell you the perfect, 2 to the power 4 or 3 to the power 4.
1 to the power 4.
I could tell you 1 to the power 4. I could tell you 0 to the power 4 too. I don't know a ton, but I know that 2 to the 4 is 16. So 2 times 2 times 2 times 2 is 16. And that must go into here because 16 goes into 64 itself. So that's what I'm going to be working with. I'm going to say that the 4th root of 6400 is the same thing as the 4th root of 16 times 400. So I did some quick factoring there, but it's that 16 goes into 64 4 times, but we've got 100 times that. I don't know if this is the highest thing that goes in there, but I'm trying it, and we'll see what happens. So if I break this up, I've got the 4th root of 16, and I've got the 4th root of 400. This part I know I'm going to get a whole component out of. 4th root of 400, though, it might still have a perfect 4th in it, and that's where I'm going to need to do some checking. 1 obviously goes into everything. The next perfect fourth is 16 again. And 16 does go into 400. In fact, it goes in 25 times. So this part stays same. And then 400 is actually 16 times 25. So there's how everything got so broken up. And I can write that as the 4th root of 16 times the 4th root of 16 times the 4th root of 25. So just follow with the colors to see how things got broken up. And in evaluating, I can say this is 2 times 2 times the 4th root of 25. And those whole components are just 2 times 2, which is 4. And we've got the 4th root of 25. This thing, I want to use a different color, is done. That concludes all of our examples for the day. If you scroll down, and by scroll down I mean use your eyes and just look down on your page, you'll see some practice work. Kind of the practice work that makes all mathematicians around the world say, ooh. It's beautiful.
And hopefully it'll also make you go, ooh, it's beautiful when you try it out. Out. And for now, we're also peacing out.